G'day, in this video we're going to be looking at the Big Bang and the expansion of the universe. This video will cover content from dot points 8.1.1 and 2. We're looking at evidence for the origins of the elements. And so in this video we're going to be looking at our best collective explanation for how matter itself formed. And that explanation is the theory of the Big Bang. So there are two major things that we're looking to try and do today. We're trying to outline a bit of a timeline for the Big Bang and describe some of the key events that we believe occurred. And we're also going to be looking at two pieces of evidence that we have to suggest that the Big Bang indeed did occur. So first off, let's talk about the Big Bang theory broadly. It is our best explanation of the origins of our universe, and the theory itself focuses a lot on how matter itself came to be as we know it today. Before the bang itself, it's understood that the universe began as a tiny point. We're talking, the size of a proton, that kind of scale. And essentially, it contained all of the energy in the universe. So the universe at this stage was something that was completely different to anything that's conceivable for us in our everyday world. We're talking about incomprehensible amounts of energy being packed into an incomprehensibly small space. This space full of energy is referred to as the singularity. And with that much energy and stuff packed into a tiny space, essentially the density of that energy was so great that matter did not exist at this point. The bang in the Big Bang isn't exactly an explosion, but more an inflation of the singularity and the space that it took up. As all of this energy starts to take up more and more space and it disperses over a greater volume, the conditions of the universe greatly change and lead to the transformation of energy to matter. You can find this timeline in your textbook. It might be a little bit difficult to read depending on the size of your screen, but there are some key points I would like to point out. In the center here, we can see an image which is meant to be representative of our universe as we progress through periods of time. The x-axis, so to speak, the width of this space is meant to demonstrate the volume of the universe, while the y-axis is supposed to demonstrate our progression through our timeline. It's really important to understand here that the timescale is not linear. The first half of the diagram outlines a period of time that goes for less than half an hour. And then the time that is demonstrated in the bottom half is in the scale of millions to billions of years. Therefore, what we should see and appreciate is that in a very, very, very small window of time, we can see an extremely fast expansion of space. This diagram and model suggests that the universe continues to expand, but the rate at which it expands is significantly less. One of the key things the diagram shows is that energy/matter is able to take up more and more space, and as the universe expands, that matter begins to spread. Towards the end, we see that matter begins to, instead of just being evenly distributed, cluster into areas where there is absolutely no matter and areas where there are big clusters of matter, namely stars and galaxies. As time progresses, we see that temperature decreases as energy starts to disperse and as well condense into matter. We also see that in these different sections, there are certain phenomena which occur which makes the universe become more complex. The following slides will focus on some of these key phenomena and expand on these ideas further. For these slides, you'll see up in the top corner that there is a given time period and a temperature range. I'm not going to spend too much time talking about specific numbers, but it's something that you might want to have a look at and read. I should also note that the range for temperature always starts with the larger temperature and ends with the lower temperature, because this is then demonstrating the progression of temperature as we cool through time. So the beginning of the Big Bang starts with what we call inflation. The singularity, again, which is about the size of the proton and contains all of the energy in the universe, expands to somewhere around a meter in diameter in the space of 10 to the negative 32 seconds. While this may not seem like a really large rate of inflation, it is quite extreme. We're talking about increasing the size of the universe by a factor of about 10 to the 25 in an extremely small period of time. Even though we had a rapid rate of inflation, the universe at this stage still was very, very hot and extremely energy dense. We should note that inflation continues after this point, but nowhere near the rate that we see at the beginning. As this happens, we'll see that the universe cools as the density of energy in the universe reduces. And this is the driving factor that leads to most of the phenomena that will be explained throughout this timeline. It should also be noted, though, that the Big Bang Theory itself has its limitations. We assume that inflation occurred and it occurred at this rate, but we don't have a very good explanation for why the singularity inflated in the first place. So as the universe begins to cool and expand, we see the formation of a bunch of different fundamental particles, including quarks, antiquarks, leptons, antileptons, and force particles. It should also be noted that at these time periods, not only were the particles forming, but we had conditions that were cool enough for these particles to remain stable and not transform back into energy. Through further expansion and cooling, we then also start to see the formation of hadrons, essentially gluons and quarks coming together to form particles composed of 2 to 3 quarks. It should also be noted, and this will be important very shortly, that hadrons composed of antiquarks were also being formed as well. We should also note that even though a lot of things are going on through this time period, the time period itself was still extremely short, with leptons and hadrons ceasing to form about 1 and 10 seconds respectively after the beginning of the Big Bang. We should also note too that through this period there is a significant rate of cooling that is occurring as well. During the formation of various particles and their antiparticles, there was an extremely high chance that a particle would collide with an antiparticle due to the high density of all matter that was forming in the universe. So even though we just established a second ago that we were getting to this period of cooling where the particles were able to exist without turning back into energy, this isn't entirely true because this is assuming that annihilation processes weren't able to occur. In fact, though, they most certainly did. So particles like protons and antiprotons and electrons and positrons and other particle-antiparticle combinations collided into each other, transforming this newly formed mass into gamma radiation. And this process of particle-antiparticle annihilation kept going and going and going until the antiparticles were essentially eliminated. Effectively, all of the matter that makes you and me and all of the other matter in the universe is the remains of this matter-antimatter war. Why this occurred, however, we're not too sure, and the Big Bang Theory does not account for it. Again, this is a limitation of the model as it is unable to explain why there seems to have been an excess of matter when compared to antimatter in this period of baryogenesis. Following the period of baryogenesis, where essentially there was only matter remaining, energy conditions were such that nucleosynthesis could occur between these building block particles. However, these conditions only lasted for about 20 minutes. And in this time, there was a significant amount of nucleosynthesis occurring, forming new nuclei. Under these temperature conditions, protons and neutrons were able to collide with each other and form deuterium. This deuterium was then able to interact with other particles, forming heavier nuclei. Depending on where you look, you were going to see a variety of nucleosynthesis reactions which demonstrate a variety of interactions between some of these smaller particles. In this diagram here, we see the piece-by-piece combination of protons and neutrons to form a helium-4 nucleus. This flowchart over here shows a variety of interactions between low-mass nucleons. I'm not going to get into the depths of all of them, but to help you understand how to read this flowchart, the nucleon which is on the tail end of the arrow is one of the reactants. And the second reactant will be the first nucleon in the brackets next to the arrow. The nucleon shown in the box that is next to the head of the arrow is one of the products of this nucleosynthesis process. And the particle which is shown in the second part of the brackets is the other product that goes with it. Furthermore, we can see here this process of nucleosynthesis leading to changes in abundances of a variety of different types of nuclei and nucleons. It should be noted, though, that the abundance of hydrogen barely changes in this process. While there is the formation of a variety of particles, their abundance relative to hydrogen is significantly less. At this stage, while there is a process in which there are a bunch of different particles which form, hydrogen remains the dominant species. All the processes outlined so far happened over a really short time period relative to the age of the universe. However, the next stage, recombination, takes a really long time to occur. In this stage, recombination outlines the conditions in which atoms can start to form. While for almost 400,000 years, the universe contained a variety of nuclei, mostly hydrogen, but some that were a little bit heavier, these nuclei were unable to form the stable neutral atoms that we are very familiar with today. The reason being there was too much energy in the universe to allow for Coulomb attraction between the protons and the electrons to bring electrons in, attract them, hold them in place, and form stable atoms. This was only really able to occur under conditions where the universe cooled to about 3000 degrees Kelvin. If we again take another big time skip and start to look at our timescale in the order of hundreds of millions of years, we see a transition of space being filled up with not very dense clusters of hydrogen and very small amounts of other species of nuclei as well, to the formation of stars and galaxies. Over these 100 million years or so, the atoms of the universe slowly but surely start to clump together as gravity pulls them towards each other. We know that larger masses attract with greater forces of gravity. So what begins to happen is that clusters of matter begin to pull more matter around it, making them more massive. As they get more massive, they again start to bring in more and more matter. What we end up with is pockets of the universe which have much denser matter than there was before, and pockets of the universe which are effectively empty space. For pockets of matter that are especially dense, we start to get the formation of stars, where there is enough density and energy between all of the particles that are clumped together to start to force fusion between light elements. Further to this, our clusters and pockets of stars begin to attract to each other, making clusters of stars, and groups and clusters of stars begin to attract to each other and their surrounding clusters to form primitive galaxies, big bubbles and clouds of stars. So now that we've gone through the expansion of the universe, let's start to talk a little bit more about how we know that this actually happens. The evidence that we have of an expanding universe comes from the concept of cosmological redshift. Now, we've talked about red and blue shift before in terms of the Doppler effect. Doppler redshift is not exactly the same as cosmological redshift, and there are some subtle differences between them. So to understand the evidence of expansion, we first must understand the difference between Doppler shifts and cosmological shifts. In short, cosmological redshift is the effect of an expanding universe. As space expands, the light that travels through it must also expand, meaning that the wavelength of the light gets larger and larger and larger as the universe itself expands. It is this concept which is being demonstrated in the animation shown on this slide. As we track and follow light that is emitted at the beginning of the universe, we see that the color of the light shifts from blue to red as it moves through the universe. The reason why this is occurring is because, again, the wavelength of this light is being stretched as the space around it also stretches due to the universe itself expanding. So rather than talking about redshift occurring because of the relative velocity between two objects as they move through space, we are rather talking about how light that we observe is becoming redshifted because it is moving through an expanding space that is stretching the wave or the photon out. This brings us to our first piece of evidence for the expansion of the universe, which is Hubble's law. In 1929, Edward Hubble put forward evidence suggesting that the universe itself was expanding. He was able to do this by measuring both the distance and the recessional velocities of various galaxies. Recessional velocity is the rate at which a galaxy is moving away from the Earth. By measuring the degree of cosmological redshift, he was therefore able to predict the recessional velocity of the galaxy. We should also note that the cosmological redshift was determined by analysing the hydrogen absorption spectra from the light emitted by these galaxies. When he compared his measured recessional velocity and the distances of these galaxies, he found the relationship V equals h naught d, where h naught is the Hubble constant and is effectively the gradient of this graph. What this tells us is that objects, galaxies, that are further away from Earth are moving away from the Earth at a greater rate than those closer. What that suggests is the universe, therefore, is expanding outwards. For objects that are close, because the universe is expanding, they are moving away from us, but they're not doing so at the same rate as objects that are further away from us, which will in turn expand at a larger rate. Interestingly, we can use Hubble's law to estimate the age of the universe. If we rearrange the equation for our Hubble constant, we find that h0 is equal to v on d, and that t, the age of the universe, is equal to 1 on the Hubble constant, the inverse of the Hubble constant, which could also be written as d on v. Now, this begs a question: how is the inverse of the Hubble constant equal to a time value, let alone the age of the universe? Let's unpack that now. We can always state that the velocity of an object is equal to the distance traveled divided by the time taken to get there. To rearrange for t, we can express that as the distance traveled divided by its velocity. Therefore, we can run with the assumption that the inverse of the Hubble constant is equal to a time. But what is this time? If we take that t is equal to d on v, this tells us that the time that we're measuring is the time taken for galaxies to separate from each other by d at a constant rate v. Essentially, this time that we're describing would be the age of the universe if we're assuming that the two objects that are separating from each other originally were at a distance of 0, and during the time that they've been separating at this constant rate v. We can divide d by v to get an estimate in years, and that approximates the age of the universe to be 13.8 billion years old. There is one other piece of evidence for the expansion of the universe which I'd like to unpack today as well, and that is cosmic microwave background radiation. For this one, the story goes that there were some scientists working on some radio telescope technology, and when doing so, they found this background radiation in the microwave range. And as scientists investigated this further, we found that you could detect this microwave radiation anywhere in space. And the collective work of many led to the development of this image here, which essentially is meant to be a picture in all directions, i.e. the picture of our universe. And at all points, you can detect this microwave radiation. So that led scientists to ask the question, well, what is it? When taking a spectrum of the background radiation, the spectrum shows black body-like characteristics, essentially Wien's law. If you use Wien's law for the peak wavelength, you find that this reflects a temperature of 2.7 degrees Kelvin, which is the temperature of the universe. It has therefore been determined that this background radiation was essentially all of the energy, the gamma radiation that was released at the beginnings of the universe. At the time, this gamma radiation was reflective of the temperature of the universe itself. But as the universe has cooled and there's been a cosmological redshift of this emitted gamma radiation, it has stretched to the point now where it exists in the microwave region, and by Wien's law reflects the current temperature of the universe as the universe expanded and cooled, thereby providing evidence again of this cosmological redshift, which has changed the wavelength of light due to the expanding of the universe itself. And so that brings us to not only the end of Module 8, but the end of the HSC course itself. I'd like to thank you for taking the ride with me on this wonderful HSC adventure and wish you all the best as you start to prepare for your HSC exams. But until then, have a good one.